Hello everyone, welcome. This is the video for the ECE 451 of the class of this Monday, the coming Monday. Tomorrow, it will be November 20. Yeah. In this lecture, we will discuss the discrete time system and state space. Yeah, similar with the continuous case, use a matrix way to represent the system. But they have something not exactly same. Now we can see what are the details. Okay, so we consider the discrete time system in state space. This part, the material in this part will not be included in the final exam. You can find them in another textbook. Remember, in the beginning of this semester, I introduced we have several books. One book is a textbook we must have. That is we already finished. We already finished those materials. We were covered in that book. And then this one is another textbook. Is for the discrete time systems. It's a kind of a reference, and this material, this kind of topic, I will not include them in the final exam, but might be useful for some students, or maybe interested by some students. So I introduce here. All right, and I will not give any assignment homeworks related with this topic. If you are interested, you can just find some problems from that book, that textbook. About the discrete time system textbook. It includes a lot of good problems you can practice. Alright. Okay, so now the system can be written in a matrix way. It looks like this way. It is x of n plus 1 equal to a times x of n plus b times u of n and y of n equal to cx of n plus d u of n. You see, similar, right? Similar with the continuous times case, we have several matrices and state variable. Now here xn will be x1 of n, x2 of n, I use k for the dimensional of the state, and like this. So this is a x, and the b is we just suppose a single input, single output case. So this just one, this is just one. Okay, and a now will be k by k matrix, right? And b will be k by 1 matrix, or a column vector, and C will be 1 by k vector. It's a 1 by k matrix or a row vector, and D is just like a 1 by 1. This is a single input, single output case. Yeah. For MIMO system, similar. You can try it by yourself. All right. Now how to solve them? Like the system style looks like this. Now how to solve them? If u of n is given, how to get x and y? So we can perform z transform. See, this is 1 by z transform. The 1 will tend to be, okay, this is a z times x of z. We here n plus 1 by z transform, it will be z times x of z. Okay. Similar with the derivative of a function after you apply the Laplace transform. And this side is a times x of z plus b and u of z. Here's y of this one doesn't matter. Okay, I put it y of z equal to cx of z plus d u of z. Then from the first equation we can have x of z equal to I move a to that side, there will be zi minus a inverse times b and u of z. And y of z, we plug in here, that will be c times zi minus a inverse b plus d, the u of z. Okay, we get this result in the z domain. Then perform the inverse z transform. We can have the inverse transform. We have y of n or equal to something something. Here we also have transfer function. Y of z over u of z or equal to this one put here, right? Oh, it's not fraction. It's a if you write it out, this one you have the inverse matrix, then you have a fraction. Denominator will be the determinant of this matrix, right? Similar, but here it's just the c times zi minus a inverse b plus d. Okay, we have this. Okay. So we can solve, we can find what is y of n, we can also know what is the transfer function. Yeah. And for the stability, as we discussed in last time, we can find all the poles. If all the poles they are located inside the unit circle, then system is stable, right? See? Poles of the system, they are roots of determinant of zi minus a equal to 0. Okay. And the stable, all poles pi smaller than absolute value smaller than 1. Absolute value is smaller than 1. Right? This is for the stable, the condition for stable. In general it's like this. And we can also have similar things like canonical form, like the transition, the similarity transform, and then like a CCF, CDF, and then feedback. We can have all the similar things with the continuous case. Now we want to focus on the how to, we have a continuous one. We want to find discrete time one. Okay. We have a system which is an analog system. How to give a digital one. So we say the digital for digital control. Digital control power. So we have a system x of t, then here's a not x of t, u of t as the input, and this system I described by a, b, c, d. Then we have y of t. Okay. Now we want to find a d, b d, c d, d d. This side is a u of n, and the output side is a y of n. We want to find this. This is we want to find. We want to find this. And here u of n or equal to u of nt. And y of n, now this side we can select they are same, but this one most hopefully they are same, but it might be just like these. Like we want to have these. Alright, t is the some more step, right? Some more step. So this is the digital control. We replace this continuous time system by a discrete time system, right? The u of t takes some ball, we get u of n. After we have y of n, we can go back to have y of t, an approximation of y of t. Now how to do it? Actually, we start from here. We can see what happened here, right? What happened here? For this system, we can know what is y, what is x, and then we find another x. Right here, we should have another x. This x in discrete time case. The other x is coming from this state x here, and based on this x, discrete time x, then we can have these state equations. Okay. For u of t, go to A, B, C, D. Output is y of t. We have, actually it's here, right? We have this one. Similar with this. Now is x of s equal to si minus a inverse times x of 0 plus b u of s. Right? We have this one. We have this one. This is x. This is x. So in time domain, it will be this one, the si minus a inverse Laplace inverse transform. This one we denote it as phi of t. It is also can be written as the exponential power of a times t. Okay. Yeah, we can use this one. This one more convenient, most convenient. Where? So x of t, we perform inverse Laplace transform. So this inverse Laplace transform get this one. So equal to, the first term is this one times constant. This is constant matrix. So it is just the inverse Laplace transform of this one times x of 0. So this one, it is the exponential power of a t times x of 0. And the second time, we have two term, right? Two factor. Both contain power. Both are function of s. This is a multiplication in s domain, right? It's a multiplication of two functions in s domain. So in time domain, it will be a convolution. So this is a convolution of this one. In time domain is exponential power of a t times b, and convolution with u of t. Okay, this one. I can write it in more detail. This is the exponential power of a t times x of 0, and plus this is a convolution where we integral 0 to t. The exponential power, I use a times t minus tau, then then times b, then times u of tau d tau, right? This is convolution. All right. So xn plus 1. We want xn plus 1, right? We want to have things looks like this. So xn plus 1 and yn plus 1. So here xn plus 1, which is x of n plus 1 times t, equal to a little bit confused. Both are x. Okay, I put the d here. xd at index n plus 1 equal to x. This is the original signal. X here, inside here is x of t. Okay, like this. Now I plug in here. It will be exponential power of a times t. Now t is n plus 1 times capital T. And then x of 0. Plus integral from 0, here's a n plus 1 times capital T. Then the exponential power a Here's n plus 1 times capital T minus tau. This one, another one. Okay. Then times b times u tau d tau. Alright. Here we want to write x, x n plus 1 can be write it as a combine of x of n and u of n. So can we find u of n and x of n here? Well, for x of n, you need a times nt, not a times n plus 1t. So here we want a times nt. So I can move this outside, right? This is a nt plus at. And exponential power, here summation actually is a multiplication, right? So this is a exponential power of at times exponential power of a nt, then times x of 0, right? So this will be part of the xd of n, right? Okay, I move this outside this. And this one, 0 to n plus 1 integral. For x of n, this integral will start from 0 to nt, not n plus 1. So I separate these as two integral. One is 0 to nt. Then exponential power, I also move this exponential power at in the front, and another exponential power, there will be a nt minus tau. Then more space. Okay, times here, I write it here, times, this is times b u tau d tau. Okay, this is the integral from 0 to n t, and plus the integral from, I write here, integral from nt to n plus 1t. Okay, I separate this integral at two parts. This is the first part, this is the second part. Here is exponential power. Okay, this one I don't separate because this is just this is some part actual, not a part of the x of n, right? So I just keep it, and the b u tau d tau. Okay, a little bit long, right? So the integral, I write it now. I have three terms. This one plus this one, and last one more terms. Okay, the first two terms both contain exponential power of at. So I put them together in the front, and then the input part is what? You see, move this in the front. You have this one and this one times this one do integral. It is what? It is just x of n. Now xd is d. Xd of n, or the x of nt, right? It is this one. And second part, I suppose b tau, not b tau, u tau is always u of, okay, you see, this tau will run from nt to n plus 1t. In discrete time case, here you get a u of n. Then between these, no more information about the input. The new input were given at this point. So from nt to here, we can think is we use the zero hold. We just use nt of u for the whole interval. So this one, it is just u of n for nt smaller than tau, smaller than n plus 1 tau. So this is a constant number. We consider this a constant number. It is just u of n. Then this is constant. B is also constant, so I can move them outside. Now this is the integral from nt to n plus 1t. Then exponential power a times n plus 1t minus tau and d tau and b u n udn. Okay, I put the d here, discrete udn, right? This is u of nt, and udn, you get this one. So this is x of nt. This is u at nt. Yeah, similar with the testing method. Remember, you do testing method, we also do the integral, and the last segment of the integral, we make some approximation, and we get this one. All right, now we can almost done. You see, xd of n plus 1 equal to a matrix times xd of n plus something, another matrix times b. You can consider this together. You consider this whole thing as a new b, then times ud of n. Okay. So this one I denote it as ad, and this one I denote it as vd. Am I right? Yeah, it is alright, but we still need more calculation, because you see here, this integral obviously is depending on n, right? Different n is different, but we want this is a fixed matrix, not something changing depending on n. So we need to do more investigation on this term. Actually, we can see immediately this one is independent with n. Equal to a d times xd of n plus, okay, this one now depending on n. Now make some change. I denote this part that n plus 1 times t minus tau equal to another tau. Let's say this is a gamma, for example, gamma. Here's a tau, integral on tau, right? I use a different variable tau, gamma. Then this one can be written as integral nt. When tau, the tau will run from nt to n plus 1t, right? So when tau equal to nt, this gamma equal to what? Tau is nt, n plus 1 times t minus nt. Tau is nt. So we get t, right? So here's the t. And here, n plus 1t. Now tau is n plus 1t. You plug in here, n plus 1t minus tau. Tau is n plus 1t. So gamma is 0. And here is the exponential power of a times gamma. Right? This one, whole thing, I replace it by gamma. Then d tau and the d gamma, they are what? They have a change on the sign, right? This is constant when you take derivative. So d tau will replace by negative d gamma. Alright, then times b times ud of n. Now you see, this term, no n inside, right? No n. So this one, it is a value independent with n. And here's a minus. We can move it in the front. And the integral is from t. This should be positive, which is large number, to 0. 0 is smaller number. So this integral is use a reverse direction for the integral, right? So we can change the location of these two, flip them. Then I need a minus in the front. Okay, here's another minus. Minus is a plus, so equal to a d, I keep it, plus integral from 0 t exponential power a times gamma, d gamma, n times b ud of n. Alright, now we have the discrete time system. We have xd of n plus 1 equal to ad times xd of n plus bd times ud of n, and yd of n. Actually, here nothing for y. We do not need any change. I just keep it, right. This is a c. Okay, I still write cd of xd, but this cd, it is just a c, and dd times ud of n, where cd equal to c, dd equal to d, and ad equal to exponential power of a times t, and the bd, okay, bd is the most complex part. BD is this one, so it is the integral of exponential power a gamma times d gamma times b. Alright, so we can know what is the discrete time one of the given system. And here we need more, this integral. What is this integral? So how to calculate it? Yeah, you can have like if you have you can work just integral, right? You give these as a function, then you calculate by hand. You can also calculate by computer. Now, how to calculate this by computer? We can work like this. Actually, we need both, right? This one and this one. We want both. We want both. So find AD. It is a exponential power of AT. That will be I plus AT. The Taylor expansion, Taylor formula is 1 over 2 A squared T squared plus 2 times 3, that will be 6 A cube T cube. Generally, it will be 1 over some m factorial A to the m T to the m. Looks like this. And every term, when m is large enough, this value will be very small and almost equal to 0. So you calculate like 1, 2, 3, 4. You calculate the first 4 terms, then all the rest you can think they are, if they are very very tiny, you can just you stop at it. If this is still somehow large, you add 1 more. But after finite terms, you will get new term will change nothing. Then you can stop. So here you can calculate by this way. You use computer, all the numbers, right? All these are numbers, matrix of numbers. And then the second one, this one, what it is? Okay, find BD. Basically, we need to find this integral. And this integral, we know the exponential power, we can write it as a series. And each term in the series by integral, the variable is this tau. So we can have this. We know exponential power of a gamma equal to I plus a gamma plus 1 over 2 a squared gamma squared. General term is 1 over m factorial a m gamma m plus, now here gamma is variable. So the integral of exponential power of a gamma d gamma is just integral of all of these terms. Gamma is the variable. So we're equal to, this is I, then it will be I gamma, right? And A gamma, that will be 1/2 A gamma squared. And this one will be 1 over, actually it's 3 factorial. A squared, keep it, and gamma cube, right? And so on. In generally, it will be a term looks like m plus 1 factorial, 1 over m plus 1 factorial, a m, and the gamma m plus 1. Like this. Okay, then now we want integral from 0 to t, right? 0 to t, exponential power a gamma d gamma. We just replace all the gamma by t. Subtract, we replace all the a gamma by 0. That is totally 0. So we only need a t verified. So this one equal to I times t plus 1/2 a t squared plus 1 over 3 factorial a squared t cube plus 1 over m plus 1 factorial a m t m plus 1. Yeah, similar in both cases. When m large enough, 1 over m factorial a m gamma m is almost equal to 0, and 1 over m plus 1 factorial a m gamma m were close to be 0. Makes sense, right? Because numerator, when m increased by 1, you will multiply more a, multiply more gamma. But the denominator were divided by m or m plus 1. So you times some fixed number, a and gamma, and divided by an increasing value. M plus 1 is increasing. The denominator is increasing. Every time you multiply a larger denominator. So when m large enough, this denominator could be very large, and every time you divided one more large number in denominator, and numerator you just times a and gamma, fixed numbers. Oh, here I plus 1. Yeah. So both will tend to be 0. So when you calculate, you only need the first few terms. Both. Okay. So when you have these, you times b, you can have bd. And by this one, you can have AD. So you can have both AD and BD. Of course, this kind of calculation is hard to perform by paper in hand. You need to use a computer to do it. It's too many terms, right? Too many calculations, especially for the size of the matrix is large. Yeah. So we can use computer to do this. And in the computer, we really have these kind of functions. All right, we can have a look. This one. Okay, here let me start. I give a system. I just use let a equal to whatever. I use a -2 and 0, 2 by 2, 0 and 0, -3. Okay, this is A. Yeah, this is the most simplest case, right? It's a diagonal. It's a diagonal one. And B equal to 1, 2, and C equal to like 2, 1. Yeah, just reverse that. D 0. D equal to 0. Then we have a continuous one. I have G equal to, now it's a SS of A, B, C, D. Right. This is a continuous one. This is a continuous one. And then we give a T, like T is 0.2. We can have GD. GD is, okay, we have a MATLAB command, C to D, continue to digital. We have G is already continue, and we use symbol step T. Now we have this one. Okay, so we can have the result just look like this. And here you can see A, B, C, D. C and D, they are the same as previous C and D. The continuous continue. This is a given one. Continuous, I have C and D is 2, 1, 0, and the discrete time is also C and D is 2, 1, and 0. We have same C and D, and A and B, they are changing. A and B are changing. And what is A and B? Here's A and B is a is calculated by the computer, right? By that function. Now we can also try to calculate by ourselves, and we can see what will happen at the same. Okay, so we have A, and we want to calculate the exponential power of A. You cannot use this exponential power of A times T. That's different. This is the exponential power element by element. You see, you will have this one. It's not this. It's not the A. It's not this A. It's not this A. Right? Here's 0, 0. Now you have 1 and 1 here. Actually, these two numbers are good. These two numbers are good. You see, here's a 0.6703, 0.6703, and this 5488, 5488. They are all right. But here's 1 and 0. Now we can calculate. Use our Taylor formula way. That is, I say this is a AD equal to, it will be I by 2 by 2, right? This is I plus 1/2, 1 is A times T, and plus 1/2, 1 over 2, then times A squared times T squared, right? And plus, okay, we can try, then they will be 6, then times A squared and A cubed, and times T cubed. Okay, I calculate 3 terms what it is. You see, I get it's somehow close, right? 6693. This is 6703, right? It's quite close. And here's a 0 and 0. This is right one, right? It is this one, right? It's quite close. I already calculated 3 terms. If I give one more term, yeah, I can copy these. Okay. One more term. T cubed plus, now it's 1 over 4, 6 will be 24. I give one more term. And here's a 4. And here's a 4. I give one more term. The result will be more closer. You see? Yeah, even closer to the answer, right? The answer should be similar like this. Just replace 1 by 0. You see? Yeah. Okay, and you can also see what is a BD. BD, we need a BD. Okay, I start from AD, similar with this AD, but here's BD. BD equal to all of these times B, right? But the formula here, I have the formula in the note. Let's go to see the formula. We need this exponential power, right? Yeah, this one. We need this one times B, right? This one times B. It's this integral times B, and this integral, the first term is I times t, then half a t squared. So actually, is you can move one t outside, you get exponential power of a t. Just times exponential power times t, then times b, right? So here I can put the t in front of it. So out of these, I times t in front of it. T times. Okay, this should be the right answer. And okay, and what did that be? This is 1.134.219 1648 16 and point. Oh, is not enough. We need more. Anyway, let me see. Right, times t. Is that good? 1, 2. Oh, I'm sorry. Now I cannot just like times t in front of it. After I time t, we compare here. I time t in front, so I plus half of a t, and 1 factorial of 3, then a squared t squared. Okay, so the coefficient is also changing. Yeah, coefficient. This one should be 2. So here should be 1 over 2 as a coefficient. And this one, coefficient here, this is 1 over 2 as a coefficient. And the second one be 1 over, now is a 3 factorial, so this is 6. And here, this will be 4, 6 will be 24. And 24, we need to times another, this will be, let me see, this is times of 5, this is 120, right? 120 factorial of 5. Okay, I think this time will be good. 1648 and 3008. Yeah, just this. You see, 1648 3008. You see? Yeah. So of course you use just C to D. You do not need to calculate by your own, but you should know what it is, right? Okay. Now we have two systems. We have G and we have GD, right? Two systems, and we can see the step response still compare with that. So step of G, and hold on, so I can job them together in the same picture, in the same graph. This is the GD. You see? Yeah, same thing, right? So both systems give the, now of course not exactly the same, but when this step, now our step is 0.2. If step is small enough, these two step response were almost same. Yeah, almost same. Actually, not just step. We use step as a test. You choose different thing, you get same thing. You'll get same thing. All right. Okay. This is how do we get the discrete time approximation of the continuous time system in the state space. we can just work like this. Okay, I think that's all for today. We have some other things like feedback, like we can have feedback, we can have the observer, for the similar thing with the continuous case. For the discrete time system, we can also have these, and we will discuss that part later next time. All right. Okay. Thank you for not coming. Thank you for the watching my video. Bye bye. See you next time.